Welcome to problem 3. Problem 3 has some easy parts and some hard parts. And for instance, part 1 is super easy. Let me scroll up here. So basically, part 1's addition maps these three properties automatically. So all you have to do is go through them one by one. Now for part 2, to prove reflexivity, notice that if you have A is related to A in the integers, then you also have A minus A equals 0 for all A in the integers. And this, of course, divides 3, so this relation has to be true. If you want to prove symmetry, then you have to first assume A to B is true, which means that A minus B equals to 3m for some certain m, and then A equals B plus 3m, B equals to A, B minus A equals to negative 3m, and B minus A is divisible by 3 for some m in integers. So this proves that relation, and finally you want to assume A is related to B, B is related to C. This gives you A minus B equals 3m, B minus C equals to 3n, based on the fact that they're divisible, right? And you add these two equations together, you get A minus C equals to 3m plus n. And this, of course, is divisible by 3, which completes part 3. Part 2. For part 3, I'm getting ahead of myself. For part 3, I actually proved this by transitivity when I first did this homework, so why don't we try that? You assume again, you have A to B, B to C, so then now you have A plus B equals 3m, B plus C equals to 3n, and notice that there's no simple addition here, so you end up with A plus 2B plus C equals to 3m plus n, and A plus C equals to 3m plus n minus 2b. Now, if B is not divisible by 3, then this fails, but we need to do this for all A, B, C in the integers, so obviously this whole thing fails. And so for part 3, there is no equivalence relation. Let me clear this up really quickly. Part 4, whenever you see the fact that you need to prove two sets are equal, then pick a random element from one set and try to equate it with another. So show that it has to belong to another. So for instance, we have A. We want to pick a C and A. And what property does the C and A have? So A is related to C. And notice that we have an implication we want to prove, so we can assume A is to B. And now by transitivity, we have B goes to C. You can flip this BA to see this. So then B is related to C, and so then there exists, right? Since the set contains all the elements, so A and A, for which B goes to A, you can see that C is one of them, and so C is equivalent to this C. Well, this C that's originally from this here is equivalent, and so you've proved that they have to be equal. And all elements are like that, so you can say A equals B. If you want a more formal proof, then go to the written solutions. Excellent. So now part 5. Part 5, the written solutions prove it by contradiction, but I can actually also prove this by contraposition. I just got to be a little bit more careful. So here, we want to assume that A and B have something in common, part 5. And let this common element be C. So C is in A, and C in B. Excellent. So now, we know that because it's in A, we have AC, and because it's in B, we have BC. And this means that by transitivity, we can flip things around, right? See B by symmetry. In the end, we get A is related to B, and this is the Q we wanted to prove. So the contrapositive is if A and B share then this has to be true, and we've just proved that. So that's part 5 of problem 3. Welcome to problem 4. Problem 4 is actually very straightforward, so I'm just going to make some comments on what's in the written solutions. So, and part 1 you could probably find in your data structures course or whatever. Let's just move on to part 2. So part 2, how do we know that we need to use strong induction here? So part 2 brings up an interesting idea in that in our inductive step we can have cases. So we can have the case that D is odd, and unfortunately it doesn't stay, or D is even. But in order to prove these two different cases, right, we need to eventually have different inductive hypotheses. And in order to do that, we need to make sure that we have a strong inductive hypothesis so that we can take advantage of all of these assumptions at once. Now, for strong induction with cases, of course, you will probably need multiple base cases. And this is absolutely fine because you're going to build things like layer by layer like this instead of where you'd go something like that earlier in induction. As long as you have places covering these steps, then you should be good to go. I believe there's not much more to cover here except for the fact that strong induction is very useful. In fact, the stronger your assumption, the more adventurous you can be with recursion or induction. And this strong induction really helps you in problems 6 and 7. Welcome to problem 5. This problem has a really long equation, but as long as you stick to your first principles, you should be fine, and this is in fact a test question that you should expect. But really, if you just follow the basic guidelines of induction, you should be okay. The homework solutions say that n equals 1 does not work, and it's always good to keep an eye out for geometric series, especially in this course. So let n equal 2, then you get, the right-hand side is easier to start off with because you can simplify it. So we get 2r2 plus 1 over r minus 1, r squared minus 1 over r minus 1 squared. Now multiply top and bottom, you know the drill. So the hard part is simplifying this really. So you have r minus 1 squared, and on the top here you have, let's see, 2 to the r4 minus 2 to the r cubed minus r cubed plus r. So notice how these two groups are already there staring at you in the face. You get this r squared minus 1, and now you have a difference of squares. So that's really convenient because now you have r plus 1, r minus 1, and r minus 1 cancels out. Excellent. So you have 2r cubed minus r squared minus r over r minus 1. And again, you can simplify again. You actually get r to r squared minus r minus 1 over r minus 1. This equals r to r plus 1 r minus 1 over r minus 1. So these r minus 1 cancel out. You get 2r plus 1 equals to 2r squared plus r. Notice how this is, I to the ri for I equals 2, and this is also I to the ri for I equals 1. So now you can put this in a summation. Of course, you can start with 0. Doesn't really matter. I to the ri. And check mark. This is the base case. Now, I'll take you some time to soak this in. Let's chug on with the algebra. So, clearing this out, we want to assume, sorry, forgot to get the pen here. And, well, we assume this, right? And instead of doing algebra this late at night, all I want to do is show you the trick that is in the homework solutions. Highlight this trick because it is actually very useful. So then when you want to do an inductive step on a summation, you should start with the original summation and actually expand out an extra term. So I equals to the sum of I equals 0, k I times ri. And now we have this extra term outside of the summation, k plus 1, r to the k plus 1. Okay, and then now all you have to do is get the right-hand side with this extra term from k, with this extra term rk plus 1, k plus 1, and try to get it to right-hand side from k plus 1. Easier said than done, but the homework written solutions really do a nice job of illustrating how to get there using the algebra. So let's move on to the next problem.